Okay, so just to recap, the solution is to apply 1 over 11 times row 1 plus 1 over 8 times row 2, 1.5 times row 3 to get all the common factors out. Then you just use row operations to bring it to echelon form and take the product of long diagonal entries, and then you can check this. Check with WH maxima or other system. Okay, well, the other thing we can do with what are the other things we can do with this is look at the determinants of elementary matrices. So if I look at the elementary matrix, say a 3 by 3, let's say I look at 3 by 3 matrices, doesn't really matter, it's going to be the same anyone. But if I do say 5 row 1 plus row 3, that elementary matrix is given by operating with this row operation on the identity matrix, right? Well, here's the identity matrix, but 3 by 3 one, and 5 times row 1 plus row 3 is going to bring a 5 down here, right? And so the question is, what is the determinant of this matrix? Well, one way to see that is to say that the determinant of this matrix should be equal to the determinant of the transpose, right? Is equal to the transpose of this one. We just asserted that. We mean the proof is in the text, but doing the transpose would just move the 5 over here, making it upper triangular. So in this case, it's just going to be 1. So, and this is, let's see, where we'll just point you to the section of text. Where in the properties, after you do the properties, it goes, let's see, where does it, no, I've misjudged where it is, yes. Well, it's not that long a chapter, just scroll down to the place. There is what I'm, okay, consequent, this is what I wanted, okay. Well, here's the point. The determinant of this is the notation for a row combination that multiplies basically k times row I plus row j, okay, is 1, right? So, and you can see that if this was like a minus sign, so the number was up here, it'd just be automatically upper triangular. So, and you can see this doesn't really depend on the 3 by 3 nature. It could be any. So any row the matrix that implements the row combination operation has determinant 1. What that means is, as the text points out, if I have E 5 row 1 plus row 3 times any matrix A, that's equal to the product of the determinants, which just equals the determinant of A. So this had to be the case, right? Because if I do a row operation on A, it's not supposed to change the determinant. So that result is consistent with what's required to have this determinant be 1. Now, if what happens if I do E row I swaps row J. Okay? Well, I started off with say if this was 1 and 3. So if I started off with the identity matrix, this is row 3, row 2, and row 1, right? Well, you can see that let's see, how will we do this? Well, this is the matrix that implements a swap. But now we've assumed that swapping the rows on the determinant introduces a minus sign. So if I take this matrix and do it by implementing a row swap, this is going to equal minus 1, 0, 0, 0, 1, 0, 0, 0, 1, which equals minus 1. The point is that if the matrix that implements a row swap is the identity matrix with 2 rows swapped. So it's kind of a determinant of that. I just swap the rows back with a minus at the cost of a minus sign to get back to the identity matrix, which is minus 1. So the determinant of the row swap operation is minus 1, which corresponds to the fact that if I act with this on another matrix, I have to get minus the original matrix back. So this is consistent with also the property that we need to have those properties originally there. So the only remaining one is E times K times row I, which is going to equal 1, say if this was 2, K1, and this is just going to equal K times the identity matrix, so which equals just K. And again, if I act with say E row K times any matrix A, well, this implements the operation on A. So we know our principle is that we can factor out that K. So this is just going to give us K times A. So this has to be the determinant by the fact that the product of the determinant of the product is the product of the determinants. So we had to have these results in order to for the original properties to actually hold true. This is more of a consistency check in that sense. Okay, now the point is then that what are the consequences of this? Let's say we have A is non-singular. And that means it's reduced to echelon form. This is say an n by n matrix, right? So because these are n by n matrices because we want to do just with determinants. Well, the reduced to echelon form is the identity matrix, and I could act on them, say by a bunch of row operations on A to bring it to reduced to echelon form, the identity matrix. So it has to be a series of like these row operations of R1, R2, R3, R4, right? So then since since row operations are elementary row operations, they all have inverses. So they all have. So we can sort of write this. We can multiply both sides by R4 inverse to move the R4 inverse over here. Gets rid of this, multiply by R3. So we're going to end up with A equals identity, R4 inverse, R3 inverse, R2 inverse, R1 inverse. And in fact, this product is in fact A inverse. So anyway, you can see the order changes here. Okay, but then if I take the determinant of A, that's going to equal the product of the determinants of the inverses times 1 of these row operations. Now, for the row swap and the row combination operations, the inverse doesn't give any, isn't going to give, it's not going to be any different. It's still going to have determinant 1. So the only factors in here that are going to occur are the possibilities of -1s for a row swap and a scaling factor. Okay? So that's just interesting that you can then look at consequences that if you were told what the row operations were, you can find out what the determinant of the matrix is. And the same way, for example, if you're given these 4 row operations, do you realize that this product here, A inverse equals R4, R3, R2, R1. So then you know that the determinant of the inverse is just the product of the determinants of these 4 entities. There's a bunch of exercises on regex and the concept checks and demonstrations that you need to have this insight that this is possible because it's asking you what is A or what is the determinant of A or something like that. I mean, you can find out what A is, right? Just from knowing the row operations that produce it. Because sort of undoing the, if you can move it to reduced echelon form, you can also structure the area matrix and move it back if you know what the row operations were. Okay, so that is a set of things you can do with these consequences. And then, in fact, these ideas are used as, for example, if you want to prove the determinant of the transpose equals the determinant of the matrix, then you use this, you want to use this expression here, right? Because you end up then messing with this, like with the transpose, there's some nice properties that have to do with the fact that the transpose of a product is the product of the transposes. So if you express A as a product of elementary matrices, then the determinant divides up into the product of the determinants. The transpose is then going to be the product of these matrices in the opposite order. But then if I take the determinant of that, I get just the determinant of the transposes. Then we can look at the elementary matrices and see that you have you end up with this being true. So as a result, you have that the determinant of the transpose is equal to the determinant of the original matrix. And you use this sort of property to get, so you take the determinant of A, write it as this, and then the determinants are just product of numbers. You can reorder them, and you end up with, there's a missing parentheses here, but you can just end up transforming it into this. And there's a case. This is the case where it's non-singular. Then you can do the singular case works. If the determinant of A is 0, you can show that the determinant of the transpose is also going to be 0. Okay, and then so you have those consequences. And there's some little problems that you can do with that. Okay, the last thing that you can sort of do with this technology, apart from finding transposes, is finding sort of special situations, is this geometry. So if I give you there's some vectors given as say let's see. Here, this would be minus 3, 2, say. I haven't drawn them to scale. Let's say you have these two vectors here. So what matrix has a determinant that is the See, you can do, let me put this over here. You see, what did I say? Three. No, X is 3 and Y is -2, something like that.
Oh, negative 34, but that's.
Since this, what did I do? I did put the minus sign in the wrong place the first time, right? So I meant 3 minus 2 because I want them both. So the question is, I can draw the parallelogram over here and ask what matrix gives this area as a positive number. So you want to choose the matrix M. So the determinant of M equals this area where it's positive. So what's the matrix? 3, 2, 4, 5. Yeah, you want to choose. So you want to sweep one angle here counterclockwise, and the one you start from is the first one, right? So you don't want to start from 4 or 5. And also the angle that you do counterclockwise is the smallest angle. See, this one is a counterclockwise, but it's the bigger of the two. So you're going to choose the smaller of the two angles. So then, and we can see then that the determinant of M is, with 2 by 2, you can just use the formula, 3 times 5 minus a minus 2 times 4, which equals 15, plus 8, which equals 23. And if I'd drawn this to scale, then you could have done that block diagram and illustrated how to done the Euclidean geometry with the formulas for rectangles and triangles, and done the standard thing to show that to calculate that the actual area really was 23 and stuff. So that's the other kind of problem. But this is basically sort of a review of everything we need for determinants. So, any questions or thoughts? If you go through and do the exercises, I think on Rex, then it'll get you sort of to the range of problems you might see on a concept check or demonstration. Now, so I wanted to do